We're going to use the greedy algorithm to start this problem. This means that in order to maximize the sum, we're going to select the largest elements to be in S. This will not necessarily get us the greatest sum, but it will be a good starting point for comparison. Since we want to maximize the sum, we're going to choose the two largest numbers to be in our set. Those are 14 and 15. If our set S contains 14 and 15, then it cannot contain the number 1 because we can produce a subset with 1 and 14 and another subset with 15, which have the same sum. With the greedy algorithm, we're going to choose the next largest numbers to be in our set. We'll add in 13 to 14 and 15. This means that 2 cannot also be in our set because we could have a subset with 2 and 13 and a disjoint subset that contains 15, the same sum. We also cannot have 12 in our set S because one subset can contain 12 and 15 and the other subset can contain 13 and 14 with the same sum. Let's add 11 to our set S. So this is what we have so far. This means 3 cannot be in S because we can produce two disjoint subsets, one that has 11 and 3 and the other one that has 14. We also cannot have 4 in S because we can produce subsets with 4 and 11, which sum to 15, and same with 5. If we try to put 10 into our set S, checking, we see that if we have one subset with 10 and 14 and another with 11 and 13, that's going to contradict the problem statement. And we can also eliminate 9 because 9 plus 15 is the same as 11 plus 13. So far we've included or excluded all of the numbers from 1 to 15 except for 6, 7, and 8. So let's add 8 to our set. So now our set contains these numbers, and checking, we see no contradiction. But if 8 is in our set, we can't have 7 in it as well because 7 plus 8 is the same as 15, and we can't have 6 either. And if we exclude 8 in favor of 6 and 7 to get a higher sum, our S would look something like this. But we see our contradiction with a subset containing 6 and 7 is going to have the same sum as 13. So our current maximum sum for S, containing these 5 elements, is 61. That's our number to beat so far. Can we beat 61 with 6 elements instead of 5? Let's calculate the number of subsets of a set with 6 elements. If all we count are the subsets that contain either 1, 2, 3, or 4 elements, that's going to be less than the total number of subsets, or 56. And if we calculate the theoretical upper bound of the sum of 4 elements in a subset, that theoretical upper bound is the sum of the 4 highest possible elements, which amounts to 54 possible sums, anything between 1 and 54. With the number of subsets greater than the number of possible sums, we must have at least 2 subsets with the same sum. But in addition to having the same sum, they must also be disjoint. So for example, these subsets have the same sum, but they are not disjoint. We can achieve a disjoint set by removing the common element in both of these subsets. And now we have 2 disjoint subsets with the same sum. Therefore, sets containing 6 elements or more will not satisfy the problem statement. So let's confirm that there isn't another set of 5 elements with a greater sum than what we calculated using the greedy algorithm. For example, let's exclude 15 from our set. Then the theoretical upper bound of the sum of that set is going to be the sum of the remaining 5 largest numbers. This is equal to 60. Switching out any of these elements in order to comply with the problem statement will only give us a smaller sum than this upper bound. We'll try to exclude 14 and calculate the upper bound of the sum without that number. So what remains are 15, 13, 12, 11, and 10. This adds up to 61, which is not greater than what we found previously. So let's exclude 13. And now the theoretical upper bound of our sum are these 5 numbers. This adds up to 62. So let's see if we have a contradiction. And we have that a subset containing 15 and 11 will have the same sum as a subset containing 14 and 12. If we exclude 11 from our set, the upper bound of our sum will be all of the largest numbers except for 11. Here is the upper bound of our sum, but as we found earlier, 13, 14, and 15 are in our set S, then 12 can't be in it. So we'll revise this, and we get a contradiction here. And anyway, this is equal to 61, which wouldn't have exceeded our previous sum. So we've not been able to exceed our sum by excluding these elements, 15, 14, 13, and 11, which leaves us with 6, 7, and 8 as before. So 8 has to be in our set in addition. So our maximum sum of our set S is 61. If you'd like me to solve any other math contest problems, please leave them in the comments.